GPT, or the Generative Pre-trained Transformer, is a powerful natural language processing model that can generate high-quality text in a wide range of applications. It is based on a type of neural network called a transformer, which allows it to learn the complex patterns and relationships between words in a sentence. To understand how GPT works, let's start with the basic idea behind neural networks. A neural network is a type of algorithm that can learn to recognize patterns in data, similar to how our brains learn from experience. For example, a neural network can be trained to recognize images of cats by analyzing thousands of pictures of cats and learning to associate certain patterns, such as the shape of the ears or the color of the fur, with the label cat.
For a rock, and this is what a rock looks like. And we could get hundreds or thousands of images of people doing a rock, so we get diverse hands, diverse skin tones, those kind of things. And we say, hey, this is what a rock looks like, this is what a paper looks like, and this is what a scissors looks like. And if a computer can then figure out the patterns between these, and can be taught, and it can learn what the patterns is between these, now we have machine learning. Now we have an application, we have a computer that has determined these things for us.
In the case of GPT, the neural network is trained to understand the patterns and relationships between words in a sentence. This is a challenging task because the meaning of a word depends not only on the word itself, but also on its context and the relationships between other words in the sentence. To overcome this challenge, GPT uses a self-attention mechanism that allows it to understand the relationships between all pairs of words in a sentence, based on their embeddings. Word embeddings are numerical representations of words that capture their semantic and syntactic properties, and are learned by the neural network during training on a large corpus of text data. The self-attention mechanism works by computing attention weights between all pairs of words in the input sentence, based on their embeddings. The attention weights represent the relevance of each word to the others in the sentence, allowing the model to capture the context and relationships between words. To understand how self-attention works, imagine you are at a party and trying to have a conversation with a group of people. If you only focus on one person in the group, you may miss important information or misunderstand the context of the conversation. However, if you pay attention to everyone in the group and how they are interacting with each other, you can better understand the conversation and contribute to it more effectively. Similarly, the self-attention mechanism in GPT allows the model to pay attention to all words in the sentence and understand the relationships between them, rather than focusing on just one word at a time. To understand positional encoding, imagine you are driving to a new city and trying to find a specific building. If you only have the address of the building, you may not be able to find it if you don't know the layout of the city. However, if you also have a map of the city that shows the location of the building, you can use both the address and the map to find the building more easily. Similarly, the positional encoding in GPT allows the model to use both the embeddings and the positions of the words to understand the meaning of the sentence. In this kingdom, the words themselves were the citizens, each with their own personality and characteristics. Some were happy, some were sad, some were loud, and some were quiet. GPT-3 could understand each of them and knew how they interacted with each other. But as the kingdom grew bigger, GPT-3 had a hard time keeping track of all the words. The more words there were, the harder it was to remember how they all related to each other. This is where embeddings and positional encoding came in to help. Embeddings were like name tags that GPT-3 could attach to each word. Each name tag contained information about the word's characteristics and personality, making it easier for GPT-3 to remember who they were and how they related to other words. For example, the name tag for happy might include information about how positive the word is, how frequently it's used, and what other words it's often associated with. Positional encoding, on the other hand, was like a map that GPT-3 could use to navigate through the kingdom. It helped GPT-3 keep track of the order in which words appeared in a sentence or paragraph. Without positional encoding, GPT-3 might get confused and mix up the meaning of a sentence. Together, embeddings and positional encoding helped GPT-3 understand the nuances of language and generate coherent sentences and paragraphs. They made it possible for GPT-3 to process and remember the vast amounts of information in the kingdom of words. Thanks to embeddings and positional encoding, GPT-3 could converse with the citizens of the kingdom with ease, understanding their unique personalities and how they related to each other. GPT-3 is a state-of-the-art natural language processing model that is capable of generating high-quality text and performing a wide range of language tasks. To achieve this level of performance, the model was trained on a massive dataset of text known as the GPT-3 training data. This dataset consists of over 500 billion tokens of text from a variety of sources, including Common Crawl, web text, books, and Wikipedia. To put this in perspective, a token is essentially a word or piece of punctuation, so 500 billion tokens represents an enormous amount of text. To give you an idea of how much data this is, imagine if you were to read 1 token per second without stopping. It would take you over 15,800 years to read all 500 billion tokens in the GPT-3 training data. Of course, GPT-3 doesn't simply read through this data once and memorize it. Instead, the model is trained through a process known as epochs, where it goes through the entire dataset multiple times, adjusting its internal weights and biases with each pass. The number of epochs used during training can vary depending on the specifics of the model and the task at hand. To use another analogy, imagine if you were trying to learn a complex dance routine. You wouldn't simply practice it once and expect to remember it perfectly. Instead, you would practice the routine multiple times, making small adjustments each time until you had it down pat. Similarly, GPT-3 goes through the GPT-3 training data multiple times, gradually adjusting its internal weights and biases until it is capable of generating high-quality text and performing a wide range of language tasks. What are parameters? To understand parameters, let's start with the basics. At its core, GPT-3 is a neural network that is trained on a large dataset of text. During training, the neural network adjusts its parameters in order to learn the patterns and relationships within the data. These parameters are essentially the values that the neural network uses to perform its computations. For example, imagine you're training a neural network to recognize handwritten digits. The input to the neural network is an image of a digit, and the output is the digit itself. The parameters of the neural network are the values that determine how the input is transformed into the output. By adjusting these parameters, the neural network can learn to recognize different patterns in the data. In the case of GPT-3, the parameters are used to generate text. The input to the neural network is a sequence of words, and the output is a continuation of that sequence. By adjusting its parameters, GPT-3 can generate text that is similar to the training data. What are layers? So, what are layers? A neural network is typically composed of multiple layers of parameters. Each layer is responsible for transforming the input in some way, and the output of one layer becomes the input to the next layer. Think of it like a stack of filters. Each filter takes in some input, applies some transformation, and outputs a modified version of the input. The output of one filter becomes the input to the next filter. By stacking multiple filters together, you can achieve complex transformations of the input. In the case of GPT-3, the neural network is composed of multiple layers of parameters. Each layer is responsible for transforming the input in some way, and the output of one layer becomes the input to the next layer. By stacking multiple layers together, GPT-3 can perform complex transformations of the input text. Do we have multiple structures of rows? Yes, neural networks can have multiple structures of rows. In fact, the exact structure of the neural network is a key design decision that can have a big impact on its performance. Different structures are better suited to different tasks, and researchers are constantly exploring new architectures in order to improve performance. How do epochs adjust the parameters to get better results? During training, the neural network goes through multiple iterations, or epochs. In each epoch, the neural network is presented with a batch of training data, and the parameters are adjusted to minimize the difference between the network's output and the correct output. By going through multiple epochs, the neural network gradually learns to recognize the patterns and relationships in the training data. This is why training neural networks can take a long time and requires a large amount of data. The more data and epochs you have, the better the neural network will perform. In conclusion, AI is a powerful tool. We all know the quote, "With power comes responsibility." This saying is true because the more power you have, the greater impact you can make. AI is an extremely powerful technology, and while technology is improving in all domains, including robotics, I can see some future job opportunities in creating robots to take over labor jobs. I don't think it will be one robot that looks like a human that will do all the jobs. This is not very smart, in my opinion. I think it will be specialized robots for each job. This will probably be an industry with job opportunities for a while, but most jobs will be taken over by robots in the future. Firstly, we will need humans and companies to come up with creative ideas to implement this technology. This will be another opportunity for the coming years, but we will slowly or quickly be getting rid of more and more jobs in the process. Why hire a person when an AI is cheaper or a robot? In time, there will be no more workers, or very few, and only the best will remain if that. Decisions may be less made in the future by companies and more by consumers. 8 years ago, I watched a video called "Humans Need Not Apply." It argued that technology would take the jobs of humans. I think that argument has gotten much stronger with recent years of advancement. So what do we do? Give up on AI and run away from it, or come up with solutions to this problem using technology? I have an idea I have been thinking about that I will discuss in an upcoming article on how to solve this problem. Furthermore, I think people may be facing an existential crisis because of this. Many people get their sense of purpose from jobs. But what will the purpose be of people if we are no longer relevant to the job market? Yuval Harari called the class who will be jobless the useless class. He is the advisor of the World Economic Forum. I think there is a solution to this problem. Harari's solution was drugs and video games to keep them busy. This is an insult to humanity. There is an answer to this question as well that I will make a thorough article about, one that I have been working on for a while about the purpose of life. It will be a very long article, but I hope it will be clear and somewhat comprehensive and persuasive in my opinion. So I hope you stay tuned for what I will be putting out in the future. I hope you have learned a lot about how GPT works.